Welcome. In this lecture, we talk about data questions. What are data questions and why are they useful in designing information visualizations? When we talk about data questions, what we mean by that is that data visualization can be used as a way to answer questions with data. Now, this is not the only possible model one can use for designing and evaluating data visualizations, but over the years, I found that it's a very, very useful model. So let me start with a very simple example so that you can get a sense of what I mean when I say that visualization can be used as a way to answer questions with data. Let's use these flight data sets. In this dataset, simple dataset, what we have in rows is the carriers, the airlines, and in columns, different hours of the day, and the values that you see inside every single cell represents the average amount of delay of that carrier at that time of the day. So now let's imagine that we have this dataset and we want to answer a number of questions. For example, when are delays more common during the day? Which airlines experience high amounts of delays? Do all airlines experience the same temporal patterns in terms of delays? These are all really interesting questions. So how do we answer these questions? One way is to create a visualization like this one, very simple line chart where every single line represents one carrier and the x-axis represents the hours of the day, the y-axis represents the amount of delay, and now we can answer these questions. So let's go through each of these questions together. When are delays more common during the day? So now with the graph, it's pretty easy to answer these questions. It's more or less between 2 p.m. and 9 p.m. with some exceptions for maybe a couple of airlines, okay? Second one, which airlines experience high amounts of delays? Well, these two here, the top ones, experience way more delays than the other ones. Next question, do all airlines experience the same temporal patterns in terms of delays? Well, yes and no. All of them go up pretty steadily, but these two have a very high peak around this time, so I would say that's a different pattern. And these two here, instead of having a peak when the others have a peak later on in the day. So that's pretty powerful. It's a simple example, but it gives you a sense of the fact that yes, visualization can be seen as a tool to answer questions that we have and we want to answer with the data. What do I mean by that? Well, every data set, it's basically a coarse representation of some reality of interest, right? Take the example that I just proposed. We're not really interested in the data. What we're interested in is in understanding the delays of a set of airlines, right? So the data is only a recording of some reality that we use to try to understand that reality a little bit better, right? So typically we have that reality, some data generated that describes aspects of that reality. Then we have data visualization, and data and the visual representation represents like the tool that we use. And then we have a person who analyzes the data through visual representations to understand that reality. So typically what we have is questions about the world, and we want to try to answer these questions with the representations that we have through the data and the visualization. And often through this process, we also generate new or even better or more precise questions. And typically what happens there is that the person who is doing this analysis has two main mental models. The first mental model is the model of the world, how the world works. And of course, this means that people who have different mental models have a different level of knowledge to understand that world, which is actually a really important aspect. And then the mental model of the data, which means what we think is in the data and what we can extract out of it in order to understand the reality better. So questions are a bridge between reality and data. So now let me give you another example. Here we use the vehicle collisions in New York City. And I will use this example to give you a sense of how we can use questions in practice when we are designing and analyzing data visualizations. Here we use, as I said, vehicle collisions in New York City, and there's this program Vision Zero, which has been going on for many, many years in New York City. And the purpose of Vision Zero is to reduce the number of collisions and reduce accidents and injuries and also people killed in the streets. And what the city of New York does is they collect a lot of data almost in real time about the collisions that happen around the city. So there's this very, very interesting and thorough data set that contains information about every single collision with a lot of different properties about these collisions. Now let's imagine that we have a very broad question, which is, did Vision Zero improve the situation since when it was implemented? You can imagine someone having this very high level question. And the first question is, can we answer this question with the data that we have? So here is a little snapshot of all the variables that exist in this data set. There are many, many, many. So for instance, we have information about the crash date, the crash time, the borough, the zip code, the latitude and longitude where the collision happened, and many, many other pieces of information. So if we have the question, did Vision Zero improve the situation since when it was implemented? That's a useful question because it guides us and gives us a specific direction in terms of what we want to do. However, what is important to notice here is that it's hard to directly answer this question with the data unless we have a way to transform this question into something that can be directly computed and extracted from the data. So there's no way to answer that question directly, because if I ask, did Vision Zero improve the situation since when it was implemented, I first need to translate this into something that I can look into the data. So in fact, what is important to notice here is that this question is ambiguous in very specific terms. Where is it ambiguous? Well, it is ambiguous when we say improve and situation. What do we mean by improve and what do we mean by situation? If we can get to a more specific description or expression of what we mean by improve and situation, then maybe we can start extracting information from the data that answer this question. So in fact, there are many ways that we can translate improve. For instance, it's before and after a date or over time. And is it everywhere or in some specific areas of New York City? And what do we mean by situation? It can be the number of collisions, the number of injuries, the number of deaths, or the number of injuries over the collisions, kind of like the injuries rate, the number of deaths over collisions, which is the deaths rate, or the number of speed tickets, or something else. So starting from a general question, we can translate it to get a very specific question that can be answered directly with the data. So what I've just described is the difference between what I call domain questions and data questions. Both are really useful because domain questions are the questions that a person working in the domain may pose to you, and the data questions are the questions that you can actually answer by looking directly in the data. And one of the main points of this lecture is that there's always a gap between these two. And it's your job as a visualization analyst and designer to figure out where these gaps are and cover these gaps mindfully and skillfully. So now let me give you a couple of examples of how a domain question can be translated into what I call a data question, where a data question is something that can be answered directly with the data that we have through a visualization. So did Vision Zero improve the situation since when it was implemented? This can be translated into how did the number of weekly injuries change during the last 10 years? So that's something that I can directly visualize and extract from the data. So if you want to pause for a moment and try this yourself, try to think about another way to create a data question from the domain question using different interpretations of what we mean by improve and what we mean by situation, which are two vague terms these terms are too vague in order to be useful to extract information directly from the data. So you can pause for a moment here and try to do it yourself, and then I'll show you another example. So here is another example of translating exactly the same question using a different data question. How did the monthly number of injuries change during the last 5 years across the New York City boroughs? So once again, starting from the same domain question, we can generate a different data question. So here is a comparison between domain questions and data questions. Domain questions tend to use the language of the domain, whereas the data questions tend to use the language of the data. There can be some connections between the two. In fact, normally there should be connections between the two, but it's important to be mindful of the fact that the language used by domain experts and in the domain tends to be vague, and you will have to find a connection between the questions expressed in the domain versus the questions that you can answer with the data. So domain questions tend to be ambiguous, very ambiguous, whereas data questions need to be unambiguous because it's the only way for you to extract information from the data and then visualize it. So they must be unambiguous in terms of what can be done with the data. Domain questions tend to be imprecise, but data questions need to be very specific. And finally, domain questions are typically not actionable in the sense that you can't directly do something with the data from them, but the data questions are actionable because they can be translated into operations that you perform on the data and eventually on visual mappings that generate a final visualization. So at this point, you may ask, why focus on questions? Why are you explaining this thing to me? What is the connection with the problem of designing data visualizations? How does it help creating better visualizations? Well, to explain that, I have to explain you a little bit this diagram, the elements that are in this diagram. So typically, what happens in a visualization project is that somebody has a problem and some goals. Right? In the example that we used so far, problem or goal could be we want to improve the situation in New York City. Very, very vague, right? So typically what happens next to that is this step that I'm talking about, generating useful, meaningful, and relevant questions. Questions that are tightly connected to the problems and the goals, right? Now, after you generate these questions can guide data collection if you need more data, but especially data transformation. So data transformations are the steps that extract from the data the information that you need to answer the questions that you have. Typically, most of the time, you need some degree of transformations, like, for instance, aggregations and computing certain statistics in order to answer the questions that you have. And the next step, you have the visual encoding step that takes this information and produce it visually in a visual representation so that it can be inspected and understood. Now, this is a somewhat simplified set of steps. Some other descriptions can add other elements in here, but I want to keep it simple for now so that you're not confused. So, one important aspect of this diagram, of this set of steps, is that every step represents a step, a moment where you can evaluate something about your design decisions. So let me show you what these are. You have 3 assessment questions. The first one is, do I have the right questions with respect to the problem and goals that I'm trying to solve? It is possible that the questions that you produce or you collect are not the correct questions because they are not actually solving the problem that the person you're working with have, right? The second one is, do I have the right data and the right information, right? Do I even have the right information to answer these questions? And am I producing the right data, calculations, and transformations to produce the information that is needed? And the final one, do I have the right representations to answer these questions? And one important thing to notice here is that if you make a mistake early on, this mistake is going to have an effect on all the other aspects. So if you don't have the right questions, it doesn't matter how good your data transformation and visual encoding steps are because you are not asking the right questions. And similarly, if you have the right questions but you don't have the right information and you're not producing the right information through data transformation, well, the visual encoding and the representation don't really matter because you don't have the right information. So it's really important to understand that mistakes in the early steps make the other steps, the quality or effectiveness of the other steps, irrelevant, because mistakes that are made early on can be recovered by the other steps. So let's simulate a scenario to walk you through these steps, once again using the New York City vehicle collisions dataset. Now, this is a very simplified scenario, super simplified. In reality, things tend to be way more complex than that, but I want to show you this scenario as an example of what can happen and how in practice using these steps and data questions can help. So let's imagine that you have this conversation and that you've been hired by some officials in New York City to help them solve vehicle collision problems using the data set that they have. So you meet these people, and the first question that you ask is, what is the problem you are trying to solve? And the official tells you, we want to reduce the number of collisions and their severity. Okay, and you go back and you ask, what do you want to do with the data you have? And they say, well, we are not sure, but we think there should be useful information there to improve the situation, right? Similar to the same question that they had before, improve the situation. What do we mean by improve the situation? Okay, so you say, all right, can you please tell me what kind of questions you have? As a side note, I found over the years that when I collaborate with some domain experts, that's a really useful question to ask. Can you please tell me what questions you want to answer with this data set? It's very effective. And the official says, yes, we would like to know what the most critical areas in New York City are. Okay, interesting. And you say, okay, good, and what else? And they reply, we'd like to know what causes the most fatal collisions. Okay, now we're getting closer to something that can be done with the data, but we are not there yet. So let's take the first one, what the most critical areas in New York City are. So now we need to translate this conversation into actions. Let me recap what we have. So the goal is to reduce the number of collisions and their severity. The domain question is, where are the most critical spots? Do you notice anything here? We have exactly the same situation as before. We have a question, a domain question, that contains elements that are too vague. What do we mean by critical and what do we mean by spots, right? These two elements can have different interpretations or different translations once we look into the data in order to answer this original question. So one possible data question that is a translation of the domain question is, how does the number of people injured distribute across the zip codes? Now, this is something we can answer with the data because we know that we have information about the zip codes and we also have information about the number of people injured in every collision. So what do we need next? Well, we need data transformation. We need to aggregate the collisions by zip code and compute the sum of the number of people injured so that we have the total number of people injured in every single zip code, which is exactly an answer to the data questions. How does the number of people injured distribute across the zip codes? And it's one possible interpretation of the domain question, where are the most critical spots? So now we map this information onto a map, a symbol map, where every symbol represents one zip code and the size and color of the circles represents the sum of the number of people injured. So we can start answering the original question. Where are the most critical spots? Or more precisely, how does the number of people injured distribute across the zip codes? And we see that there are some areas with large bubbles around here, around here, around here. So we can start inspecting this map to better understand what is going on there. Okay, but we can, as I said before, use a different data question starting from the same domain question, right? That's the whole idea in this lecture. So what is another possible data question? Another possible data question is, where are the geographical locations with a high density of collisions? So now this is slightly different. It's no longer about zip codes, and it's no longer about the number of people injured, but it's about how the density of collisions changes around the geographical area of New York City. So here I need a different type of data transformation. What I need to do is to project the collisions on the map. Remember that in the dataset I have individual collisions, and then compute a density map or a density function that basically calculates how dense in terms of collisions a given area is. And once I do that, I can create a new type of map where I project and visualize the density of collisions using a specific color map. We will talk about effective color design later on in the course. Here is a very effective color map that shows exactly where the hotspots are. You see there are some really bright spots in some of the areas, and this helps answering in a different way the original question, where are the most critical spots? So as you can see, starting from the same domain question, I can produce different data questions. Different data questions lead to different data transformations, and all of these lead to different visual representations. So, as I said before, all the choices here have cascading effects on the next levels. In particular, here I showed you that if I have a different way of translating the domain question, I typically have to produce different data transformations and different data representations. So this whole idea comes from or is inspired by very, very popular paper in visualization research, published several years ago by Professor Tamara Munzner. It's called A Nested Model for Visualization Design and Validation. And in this paper, she introduced this idea of having several steps that are nested, and they are nested because if something goes wrong at a top level, it's very hard to recover in the inner levels because there's a cascading effect of making a bad decision at the top level. Okay, so Professor Munzner uses a slightly different terminology, and it's a little bit more complex than what I presented here. So I encourage you to read this paper if you're interested, but the logic of the whole idea is the same, right? There's a problem with some goals. This needs to be translated into some questions in the model that I presented, data transformation, and visual representation. Now, another thing that I want to stress is that data questions are also really powerful because you can use them to evaluate data visualizations. How do you do that? Well, if you have a list of questions and you have the visualizations that you develop to answer these questions, what you can do directly is to check for each visualization if it is able to answer the questions that you have. So having that list of questions is really, really useful. You can literally go through every single question and see if you can answer it through one of the visualizations that you have. Step 2 is to ask yourself, can I answer the questions effectively? Okay? And here we don't have an answer yet on how to answer that question, but in the rest of the course, we will cover what we mean by effective, okay? But in general, having a list of questions is really useful because you can use it as a checklist to verify whether the visualizations that you developed answer the questions that you have. Now, you can do that in two main ways. You can evaluate it on your own using yourself as an expert, literally doing what I just said, going question by question and seeing if your visualization answers these questions. Or in a different setting, more complicated setting, you can evaluate these questions, sort of like in a usability study, to see if people are able to answer these questions using your visualizations. In either case, having a list of questions is really, really useful and effective. So practically speaking, what you will have to do is to formulate questions explicitly, and it's okay to refine them over time. Translate domain questions into data questions. Design transformations and data visualizations that accommodate that information, and then test the visualizations using your questions. And again, either using your own judgment or testing these questions with a group of users or readers. An important aspect of data questions is that the type of questions that you can ask and eventually the type of answers that you can produce with data visualization depend on the kind of information that you can extract from the data. So we have to have a way to describe the type of information that is in the data. And this is what I call data characterization. So what kind of information can be extracted from the data? If we have an effective way to do that, to characterize the data, then we can better understand what type of questions we can ask, what type of information we can extract out of the data, and eventually, most importantly for the purposes of this course, what type of visual representations we can use. So the way I like to describe that is that there are 4 fundamental types of information that one can find in datasets. Typically, these are called like different types of attributes, different types of fields, different types of variables. Which term we use exactly is not that important. You will see that I will basically use these terms interchangeably. More often, probably, I will use data attributes. But the idea here is that the elements that describe the objects that are in a given data set and in a given table can express different type of information. So typically we have four types. We have categories that can be ordered or unordered. We can have measures. We can have locations and regions, or anything that is spatial, and times and dates, which means anything that is related to time and dates. So let's review the specific types using, once again, the vehicle collision dataset. So in the vehicle collision dataset, we may have things like contributing factor, which is what contributes to a collision. And this is just a number of categories. There's no inherent order in a contributing factor, and there's no specific arithmetic operation or quantitative operation that you can do with categories. So contributing factor is an example of categorical information that you can find in a given data set. Second one, collision severity. So collision severity is also a number of categories, but in this case, these categories are ordered. So they don't measure necessarily anything specific, but they have an order. So if I say low, medium, and high, these are three values. They represent three categories. They are ordered, but they do not represent a specific quantity. The second type is measures. So in the collision datasets, number of persons injured and number of persons killed in a given collision is an example of two measures. So measures in general is just quantities that represent something that is being measured. Next one, locations and regions. In the dataset here we have borough, zip code, latitude, and longitude. And you may notice here that in this case we can have different types of geographical or spatial information. For instance, borough and zip code are categories that represent geographical areas or locations, whereas latitude and longitude are quantities that together represent a specific location through geographical coordinates. The next one is times and dates, and in this data set we have the crash date and the crash time. So now let's look at relevant properties of each type. As we do that, try to ask yourself, how do these properties influence visual representation? And more in general, what kind of questions we can ask to a dataset. So let's start from relevant properties of categories. So one of these properties we have already covered. The categories can be ordered, they can have an inherent order, or be completely unordered. So as I said, contributing factor doesn't have any inherent order, whereas collision severity has an inherent order. For instance, low, low, medium, medium, medium high, and high. Another really important aspect of categories, and that we will see is very important in visualization, is the cardinality, which means the number of distinct values that exist within a categorical attribute. The next one is hierarchy. What I mean by that is that categorical values can be organized in a hierarchy. For instance, if we look at the vehicles, we can have the vehicle brand, and within the brand we can have the different vehicle models, right? A hierarchy. So there are many categorical attributes out there that can be organized in hierarchies of 2 or more levels. So now you may want to ask yourself, why is it relevant to identify these properties in visualization? Well, later on we will see that one of the reasons why this is important is because different properties lead to preferring different visual representations. As an example here, cardinality If there are many distinct values, there are visual representations that scale better than other visual representations if I have a lot of objects, a lot of categories that I want to present at once. Or if I have an ordered versus an unordered set of categories, the way I visualize them is important because the visual representation may imply or not that there is an inherent order. Second one, we have relevant properties of measures. What do we have here? Well, measures can be unidirectional, typically from 0 to some maximum level, maximum value, or bidirectional. So for instance, the number of people injured is unidirectional. It goes from 0 to a maximum, whereas the change in number of people injured, for instance, between 2 years, is something that can have a positive or a negative value. The next one is statistical summaries. Often, the numbers that we extract out of a data set, typically through different levels of aggregations, represent some statistical properties, some statistical measures. So for instance, count, percent, sum, average, and so on. Here, for instance, we can compute the average number of people injured by borough, or any other statistic that we have seen in some of the examples that we covered so far. Another important property of measures is that sometimes measures can represent what is called a part to a whole. So every single number represents a relative number compared to a total. So part to whole, for instance, is the proportion of collisions by contributing factors. And typically, this is represented by percentages. Okay, once again, here you can ask yourself, why is it relevant to identify these properties in visualization? And the answer is, once again, that whether something is, for instance, unidirectional or bidirectional, if it's a statistical summary or not, or if it's a part to whole or not, has an impact on the way we will decide to represent this information. Why? Once again, because different visual representations have implications in terms of whether they convey the idea that something is, for instance, bidirectional, if it's a statistical summary, or if it's a part to whole. We will cover all these elements in much more detail in a later lecture. Now, relevant properties of locations and regions. So first of all, there's this idea that attributes that represent space or geography in general can represent individual locations through coordinates or all regions. For instance, point in space, like the specific location where a vehicle collision happens, is represented by the combination of two coordinates, which are latitude and longitude. But a spatial region can be represented by a name like the zip code, or in our case, a borough, and in practice on a map being represented by a whole polygon that represents the whole region, rather than an individual point in space for specific locations. Second point is that locations can be considered as categories or spatial coordinates. For instance, if I look at the boroughs in our example, we can have Manhattan, Brooklyn, and so on. And these can be used as just simple categories without a specific geographical meaning or geographical representation. But they can also be represented as polygons that describe the specific spatial coordinates of these regions. Finally, locations and regions can also have different levels of granularity, which means they can also, as well as categories and actually measures as well, generate different hierarchies or different levels of granularity. Using once again the same example, we can have data at the level of boroughs or higher granularity at the level of neighborhoods, or higher granularity at the level of zip codes, and higher granularity at the level of individual points in space, individual coordinates. Once again, why is it relevant to identify these properties in visualization? For the reasons that I already covered, because whether you consider, for instance, information as geographical or not, it may make sense to have a map or not. If you have a spatial region or a point in space, you will also make different decisions in terms of visual representation, and different granularities in terms of geographical information will also lead to representing data values, for instance, on a map at different levels of details. Finally, relevant properties of times and dates. So the first thing to say is that times and dates are composite objects. They're not just one single object, they're made of parts. So for instance, dates are made of months, day, and year, and times are made of hours, minutes, seconds, and if you want, other elements too. The second relevant property is that time is inherently hierarchical, and this means that you can represent information that is connected to time at different levels of granularity. So, similar to the geographical case, you can represent information at the level of years, months, weeks, and days, or hours, minutes, and seconds. Using once again the vehicle collision dataset, you can, for instance, look at information about people injured at the granularity level of years, months, weeks, days, or you can look at the number of people injured in collisions at different times of the day in terms of hours, or a granularity of minutes, or a granularity of seconds. The last element that I want to highlight about times and dates that is really unique to times and dates is that time can have a cyclical structure, can represent it through a cyclical structure. What do I mean by that? I mean that if we look, for instance, at the minutes of the hours, the minutes during a day, you go from 1 to 60, and then it comes back to 1. So time is circular. And hours, for instance, are also circular. The hours in a day, they go from 1 to 24, and then they start again. And once again, why is this relevant to identify? Why is it relevant to identify these properties in visualization? Once again, because these elements have an impact on the visual representations that you will use, or how the visual representation will look like if you make different choices. For instance, in terms of whether you want to highlight the cyclical structure of the data, or the level of granularity, or which part of times and dates you consider in your analysis and presentation. Now I want to go back to the original question, which was, what is the relationship between data types and questions? In fact, the whole reason why I introduced the concept of data characterization here is because I wanted to present to you this idea that different combinations of data types can help answering different types of data questions. So one simple model that I like to present when I talk about this is that there's a set of fundamental combinations that covers a pretty large set of data questions and effectively the corresponding visual representations that we use in data visualization. So one way to look at this is that most questions that we have out there can be seen as combinations of categories and measures, locations or regions and measures, times and dates and measures, where these measures can be unidirectional or bidirectional. They can represent statistical summaries, sometimes with uncertainty around them, and they can sometimes represent part to a whole, typically when they represent percentages. Now, these combinations offer only a glimpse of the kind of data questions you can typically ask and answer with data visualization, but it's a pretty powerful set of combinations. And it's here mostly to give you a sense of the fact that there is a tight relationship between combinations of data types and the type of questions that we can answer. So, when we put together categories and measures, typically what we can do with them is to rank and compare values. An example here is how do the contributing factors compare in terms of number of collisions, right? So if you compare them, you can rank them, you can compare. So that's the main thing that you can do when you put together a category, a set of categories with a measure. The second one is spatial distribution, where you put together locations of regions and measures. And an example here is how does the number of collisions distribute across the New York City area. The next one is temporal trends, a very common one. In these ones, we have something that changes over time according to a measure. An example here is how did the weekly number of collisions change over the last year. And the final one is relationships and correlations, where you put together either two measures or two categories. And an example of this one is there a correlation between the number of people injured and the number of people killed in vehicle collisions? So that's a useful categorization to keep in mind, even if it's very simple. Of course, there are way more complex combinations and way more complex questions that we can ask, but many of them are basically a more complex version of these basic types: ranking and comparison, spatial distribution, temporal trends, and relationships and correlations. So what are other types of questions and combinations? As I said, there are many more. It's almost impossible to provide all of them here. But we can have more complex measures like deviations, part to whole, uncertainty, as I mentioned briefly earlier. We can have more than two variables. So for instance, we can have two categories and one measure. Or we can have more than one measure. We can have one category and two measures, or even two categories and two measures, and so on. And of course, the more variables we have, and the more complex is the information that we represent, and the more complex are the questions that we can ask. And of course, we can also go beyond quantitative relationships. For instance, one thing that we are not covering here, and we won't cover until much later in the course, is relationships like in network data, right? In network data, we have basically data that represents relationships. There can be some quantities attached to them, but not necessarily, right? So there are data sets out there that represent only relationships without having specific categories or measures. And much more than that. So it's important for you to know there are many other types of questions, many other types of combinations, but I still think that this basic model is a very useful initial model to start thinking about what are typical classic types of questions you can ask to a data set and that you can answer with data visualization. So this concludes the lecture. I just want to summarize what we covered because we covered a lot. So we covered the role of questions in visualization design and evaluation, and I hope that I convinced you that coming up with an explicit set of questions is a very, very powerful tool for visualization design and evaluation. Then we talked about the idea that Domain questions are questions that tend to be very vague, but also very useful because they are typically gathered for domain experts. But they need to be translated into data questions in order to be answered with data and data visualization. Now, this translation very often is just done implicitly, but I also found that is often the source of many mistakes or suboptimal solutions. So what I encourage you to do is to keep in mind this idea that every time you transform or manipulate data and generate a visualization out of it, you are implicitly going from a domain question to a data question before doing that. And if you do it more explicitly, you can make more mindful and effective choices. The next one I covered is data characterization, or the type of information that can exist in a given data set. And then we covered the relevant properties of the different types that I covered. And I've been stressing quite a lot the idea that these properties have an implication or an effect in what kind of visual representations are available and possible, which is something that we will cover on a much deeper level later on in the course. And finally, I covered the idea that different combinations of data types can be used to answer different types of questions, and also the idea that there is a basic set of questions that we can ask to a data set and we can answer with data and data visualization.